Alright, so now that we are going to move on to the second section, we're going to learn about the nuclear transformations. So if you remember from the first day, I was talking a lot about the stability. So if you remember, the whole point in atoms behaving the way they are is everybody is trying to get stable. When we're dealing with ionic and covalent compounds, everybody's trying to follow the octet rule, which means they all want 8 electrons, which means they all want to look like a noble gas. But if you remember me talking about it from the first day, nuclear transformations or nuclear reactions and radioactivity don't necessarily follow these rules. The reason they're unstable is because of their ratio of protons to neutrons not being 1-to-1. So instead of trying to follow the octet rule, they are trying to rearrange their protons and neutrons to make more stable atoms. So the stability of a nucleus depends on its neutron to proton ratio. And if you notice over here on the right side of the screen, we have a graph of neutrons versus protons. And if you notice, here are all the dots representing all of the elements, and this blue line right here is representing a 1-to-1 ratio. And if you notice, as we start down here with an atomic number of 1 to 10, even to 20, they fall right on that line of a 1-to-1 ratio. But then once we hit 20 and we start increasing our atomic number, once we get to 40, it's even farther from the line. Once we start to increase to 60, it's even farther from the line. And when we get all the way up to an atomic number of 80, it's nowhere even close to the line of the 1-to-1 ratio. Which means the farther you get down the periodic table, the farther away it is from that 1-to-1 ratio. Or in other words, the more neutrons versus protons an atom is going to have. So in order to become a stable nuclei, you are found in the region called the band of stability, which is this line I was just telling you about. This blue line is called the band of stability. This 1-to-1 ratio is ideal. This makes the elements stable. Elements usually do not exceed a 1 to 1.5 ratio. These elements are unstable, and these are the ones that can be found up here, which is, if you notice, why most radioactive elements are not found at the top of the periodic table. Most of them, like uranium and plutonium and, well, I can't think of another, radon, are found towards the bottom of the periodic table. So, unstable nuclei undergo radioactive decay for several reasons. First of all, elements either want to lose neutrons through beta emission, which again, if you remember what a beta particle is, we're technically talking about the loss of an electron. So elements want to lose neutrons through losing electrons, or they want to gain neutrons by converting a proton to a neutron, and this is called a positron, which we will see in some of the practice transformations that you did earlier and the ones that we'll continue to do for this unit. The neutron to proton ratio determines the type of decay. So, when we are talking about radioactivity, we also have to talk about something called a half-life. When we're talking about a half-life, we're talking about the rate of decay, how quickly these atoms are going to decay into a stable isotope. Some of them decay really quickly and form an isotope. Some of them take a really, really, really long time. The longer it takes you to become stable, the more dangerous you can possibly become. The amount of time it takes for 1/2 of the nuclei of a radioactive isotope to decay. So for instance, if my half-life, the half-life of my soda is 10 days, it means that in 10 days, half of my soda will have decayed into something else. So if we go through 20 days, that means 75% of my soda has decayed into something else. And if we go over 30 days, then that means that half of my quarter has decayed. So it just keeps getting halved and halved and halved and halved. The shorthand for half-life is to write a T, because half-life is talking about time, with a subscript of 1/2. After each half-life, half of the existing atoms have decayed into a different element of some sort, and the half-life can range from seconds to millions of years. And the most common use that you guys will recognize is that we can use these to date artifacts. We use carbon-14, which is an isotope of carbon, because usually carbon only has a mass of 12. Carbon-14 we use to date artifacts and how old things are in archaeological digs, so on and so forth. Okay, so let's go through an example. So I just talked about carbon-14. This is the one we use to date things. Carbon-14 emits beta radiation. Again, beta radiation is represented by a 0, -1, and a lowercase e, and it decays with a half-life of 5,730 years, which means that if we start off with 10 grams of it, after 5,730 years, we're going to have 5 grams of it. If we go another 5,730 years, we're going to have 2.5 grams of it. After another 5,730 years, we're going to have 1.25 grams of it. And you just keep having your amount for every single half-life that you pass through. So let's assume that we start with a mass of 2 times 10 to the negative 12th grams of carbon-14. Again, that's a pretty small amount. The first question I'm going to ask you is, how long is 3 half-lives? So if 1 half-life is 5,730 years, how long is 3 half-lives going to be? To figure this out, you just take 3 times 5,730 years, and you get a grand total of 17,190 years. So this is an example of one of those isotopes that has a very, very long half-life. The second question we're going to talk about is, how many grams of the isotope are going to remain at the end of these 3 half-lives? So again, for each half-life, you are going to half your sample. So basically our sample is going to be halved 3 times. So you're going to do 2.0 times 10 to the negative 12th. You're going to times it by half 3 times. So your total is going to be 0.250 times 10 to the negative 12th grams. So after 17,190 years, you are only going to have 0.25 times 10 to the negative 12th grams of carbon-14 remaining. Okay, so let's try this practice. Okay, practice. Manganese 56 is a beta emitter. Again, we are dealing with an electron here, with a half-life of 2.6 hours. What is the mass of manganese 56 in a 1 milligram sample at the end of 10.4 hours? So to solve this, we have to first figure out how many half-lives have occurred. We know our starting amount, we know our total time, and we know our half-life, but we need to know how many times to halve the sample. So basically what you're going to do is you're going to take 10.4 and you're going to divide it by 2 until you get, or you're going to take 10.4 and divide it by 2.6 and you're going to get a number. So if you do 10.4 divided by 2.6, you get 4, which means that manganese 56 has gone through 4 half-lives. So basically our 1 milligram sample has been halved 4 times. So I want you guys to take a minute and I want you to try to figure out how many milligrams you are going to have left after our 10.4 hours / 4 half-lives. Okay, so we've already figured out that we've gone through 4 half-lives, and again we did this by going 10.4 divided by 2.6, so we got a total of 4 half-lives. So now we need to figure out that's how many times our 1 milligram sample has been halved. So to figure out our total amount, you're just going to take 1 and you're going to divide it by half 4 times. So 1, there's our first time, our second time, our third time, and our fourth time. So after 10.4 hours, we are only going to have 0.0625 milligrams of manganese 56 left. Alright, so let's do another practice problem. I know it's hard for you guys to follow along when I can't write on my computer screen. But let's look at the second practice problem. This time, it says a sample of thorium-234 has a half-life of 24.1 days. Will all of the thorium undergo radioactive decay in 48.2 days is our question. So again, The first step is we have to figure out how many half-lives have occurred. So 48.2, so if we take 48.2, which is our total time, and we're going to divide it by the time of one half-life, which is 24.1, we get a total of 2, which means that in this amount of time, we are going to have 2 half-lives occur. So it doesn't matter what the sample is that we're starting with. Basically, this question is just general. It's wanting to know how much of the sample is going to remain. So let's just say we start with 1. We start with 100%. Okay, so we're starting with 100%. I'm just going to use 100. It's going to go through 2 half-lives, which means it's going to be divided in half twice. So now we're at 50%. We go through another half-life. We're at 25%. So after 48.2 days, you are going to be left with 25% of your sample. So no, the entire sample of thorium will not have undergone radioactive decay. We still will have 25% or a quarter of the sample will remain. All right, so hopefully I have given you enough practice problems to get started on your homework. Please help each other get through the first couple of ones because this is a hard concept. Trying to keep the definition of half-life and total time and the amount of days and the amounts all separate is kind of tricky. But we do have a practice activity. I think there's only 4 or 5 problems, but if you actually look on the back of your sheet of paper, there's some steps because some people really like to follow steps when solving half-life problems. So I have handwritten out some steps to follow if you get stuck or you're not sure where to go. But try your best to get through these problems. Look at the steps if you get stuck. Ask your neighbor. Feel free to work on these together. Just make sure that you understand how to do it and you're not copying off of your partner.